I want you to picture something with me for a second. Imagine you are standing in the middle of a lush, towering forest.
Okay, I can picture that.
Right. And the canopy above you is incredibly thick, filtering the sunlight down in these beautiful, shifting, greenish golden beams. It feels ancient.
That sounds incredibly peaceful.
It does, right. But here is the crazy part about this particular forest. The quote-unquote trees around you are growing at an absolutely astonishing rate. We are talking up to 20 inches. That is about half a meter every single day.
Wow, so you can practically watch them grow.
Literally, they are shooting up to reach heights of 260 feet, creating this dense, three-dimensional jungle. It's a total biological marvel. But here is the twist, the punchline to this little visualization.
Let's hear it.
You aren't standing in a forest of trees at all. In fact, what is towering over you isn't even made of plants. It is kelp.
It is a profound twist, really, and it perfectly sets the stage for what we are looking at today because, well, if you look at kelp, your brain immediately registers it as a plant.
Right. I mean, it's green, it's leafy.
Exactly. It has plant-like parts. It uses chloroplasts to convert sunlight into energy through photosynthesis, just like an oak tree does. But kelp is definitively not a plant. It belongs to a completely different evolutionary lineage called straminopiles.
Phreanopiles? Okay, I had literally never heard that word before reading the sources for this deep dive.
Most people haven't. And to put that in perspective, straminopiles are this bizarre, highly diverse genetic family. It includes microscopic, single-celled algae, and even certain water molds.
Wait, water molds?
Yeah, water molds. They sit on a completely separate branch of the tree of life from the terrestrial plants we see on land.
Which completely blew my mind. You think of seaweed as just, I don't know, wet weeds. But our mission today is to explore this hidden and surprisingly profound world of kelp.
It really is profound when you dig into it.
We are going to look at how it acts as one of the greatest biological imposters on Earth, how these underwater forests literally pave the way for early human migration, and how kelp is secretly lurking in your ice cream right now.
That last one always gets people.
Oh, totally. I promise you, by the end of this deep dive, you are going to look at the ocean entirely differently.
To really appreciate kelp, I think we have to start by examining that deception you mentioned. It looks and acts so much like a terrestrial plant, which naturally makes you wonder why it would bother putting on that disguise in the first place.
Right, because if it's not a plant, why does it have leaves and a stem and roots?
Well, the answer is one of the most incredible examples of convergent evolution on the planet. Because as the research shows, it actually doesn't have those things.
Right, we just map those words onto it because of our own bias. Okay, let's unpack this. Instead of leaves, it has these flat structures, right?
Yes, they are called lamina, or simply blades. And instead of a woody stem, it has a flexible structure called a stipe.
A stipe. And then for roots.
Instead of roots digging into soil to pull up water and nutrients, it has a holdfast. And a holdfast doesn't absorb anything.
It just holds fast.
Exactly. It just acts like a biological fist gripping tightly onto the rocks at the bottom of the ocean so the organism doesn't just, float away.
Which makes sense. And then it even has a slimy mucilage layer on the outside instead of the waxy cuticle that terrestrial plants use.
Right. And the function of that slime is entirely different from plant wax. A land plant uses a waxy cuticle to trap moisture inside so it doesn't dry out in the baking sun.
But kelp is already underwater.
Precisely. It doesn't need to retain moisture. Its mucilage layer is there to reduce friction against the ocean currents and to prevent parasites and little barnacles from easily attaching to its surface.
It's like a non-stick coating.
That's a great way to put it. But the evolutionary timeline here is what makes this structural mimicry so astounding.
Oh, yeah, the age gap. Tell me about the age gap.
Well, if we look at terrestrial vascular plants, the trees and ferns we are used to, they evolved around 419 to 454 million years ago.
Right.
They have had a massive head start on figuring out how to build a tall structure to catch sunlight.
Huge head start.
The ancestors of kelp, on the other hand, are much younger. They only showed up about 189 million years ago.
That timeline difference is wild. We are talking about hundreds of millions of years of separation. I always think of convergent evolution like two completely isolated inventors coming up with the exact same blueprint for a bicycle.
That is a very apt analogy.
Right, like they didn't just stumble on the bicycle design by accident. They both realized that if you want to go fast on a flat road, two wheels is the undeniable, physics-defying trick that works best.
Yes, the environment dictates the optimal shape.
Just like kelp realized, that to catch sunlight in a fluid environment, having a sturdy vertical stem and flat horizontal panels is the best blueprint. Wait, I have a question about this.
Go for it.
If kelp evolved hundreds of millions of years later and in a totally different watery environment, why bother mimicking terrestrial trees so closely? Is this just the undeniable, universal best blueprint for life?
What's fascinating here is that it's doing something incredibly unique internally, and the blueprint isn't actually finished.
Wait, what do you mean not finished?
Well, it looks similar on the outside, and it did independently evolve its own internal transport mechanisms for nutrients. Because if you are 260 feet tall, you need a way to move the sugars you create at the sunny surface down to the holdfast sitting in the dark.
Right, you need plumbing.
Exactly. So kelp uses these trumpet-shaped sieve elements to move organics around, which is very similar in function to the xylem and phloem in a tree. But a fascinating 2015 study looked closely at the internal anatomy of the giant kelp, Macrocystis pyrifera, alongside several other species.
Okay, to see how the plumbing works.
Yes. The researchers wanted to see if kelp had the same universal allometric scaling as trees.
Okay, just to make sure we're all on the same page, allometric scaling basically means there is a mathematically predictable rule for how the organism grows. Right? Like, if a tree gets twice as tall, its internal plumbing has to get proportionally wider by a specific mathematical ratio to keep the water flowing.
Precisely. Trees have figured out the optimal universal math for their plumbing over hundreds of millions of years. But when they measured the kelp, they found no universal allometric scaling across the tested structures.
No universal scaling at all.
None. What that implies is that the internal transport networks in brown algae are still in their evolutionary infancy. They are basically in beta testing.
Oh, wow. Beta testing biology.
Exactly. They haven't settled on a universal mathematical rule like trees have. Instead, they are actively, rapidly adapting to fit their highly specific current niches. They are hacking their own biology in real time.
Here's where it gets really interesting, because that active adaptation is happening in an environment that is way more brutal than your average terrestrial forest.
Oh, absolutely. The ocean is unforgiving.
Yeah, it's turbulent, it's constantly pulling, tearing, and smashing things against rocks. Which brings us to how kelp survives that chaos. Because it doesn't just adapt its internal plumbing, it literally shapeshifts its entire body.
Yes, the scientific term for this is morphological plasticity. Kelp can physically alter its body shape based on the specific neighborhood it grows in.
Which sounds like science fiction.
It does. Because they deal with varying levels of wave disturbance, they have evolved a profound genetic plasticity for their blade shapes.
Yeah, like the giant bull kelp, Nereocystis luetkiana. The sources note that if this kelp grows in a really rough, high-wave area, it will physically alter the width, the ruffle, and the thickness of its blades to handle the drag.
Right, it makes itself more streamlined to survive the battering.
And there's another species, the giant kelp Macrocystis integrifolia, that actually has 4 completely distinct blade types depending on its habitat. To put that in perspective for you listening, it's as if you moved from a calm suburb to a windy mountain, and your body instantly responded by growing thicker skin and shorter limbs.
It is a brilliant survival strategy, but it absolutely complicates things for the people trying to study it.
I can imagine. How do you even classify something that changes shape?
With great difficulty. In biology, we call this unusually high level of morphological homoplasy. It makes classifying brown algae incredibly difficult because individuals of the exact same species can look entirely different from one another just because they grew up in different water flow habitats.
That is so confusing.
It really is. You might pull up a specimen and think you have discovered an entirely new species, but really it's just a regular giant kelp that's been doing CrossFit in a heavy wave zone.
Huh. The ripped CrossFit kelp versus the lazy current kelp.
Yeah.
I love that. And their adaptability doesn't stop at their shape. They've also figured out how to travel.
Yes, the rafts.
Right. Some species of kelp have evolved these structures called pneumatocysts. They're essentially built-in, gas-filled bladders that act like little flotation devices.
They hold the heavy blades up near the surface to make sure they get sunlight.
Exactly. But when the ocean gets too rough and the kelp snaps off from its holdfast, those bladders don't deflate. They turn the broken kelp into massive, drifting rafts.
And those rafts are highly effective vehicles for oceanic dispersal. They don't just move the kelp itself, they become floating lifeboats.
Carrying passengers.
Exactly. They carry non-buoyant hitchhiker species, little invertebrates, snails, other types of algae across the globe.
That is wild.
Through modern genomic analysis, we have recently confirmed that this is exactly how certain species achieved their massive evolutionary spread.
Really? Do we have a specific example of that?
We do. For instance, the giant kelp Macrocystis pyrifera actually colonized the subantarctic region very recently in evolutionary terms.
Why we know it was recent.
We know this because of the remarkably low genetic diversity found in those southern populations. They basically hitched a ride on these ocean currents, survived the journey because the kelp kept photosynthesizing as it drifted, and dropped down to seed entirely new ecosystems.
They're essentially shape-shifting transport ships. And wherever they drop anchor and take root, they don't just survive. They build sprawling underwater
They
megacities.
really are the foundation of these ecosystems.
I mean, kelp forests are among the most productive and dynamic ecosystems on the entire planet. The source mentioned that along the Norwegian coast alone, kelp covers 5,800 square kilometers.
That is a massive three-dimensional structure underwater.
It's huge. And the density of life in these underwater cities is just staggering.
It is. You aren't just looking at the kelp itself, you are looking at the foundational architecture for entire food webs. Down in the holdfasts, those root-like structures we mentioned earlier, it acts like a complex apartment building.
Right.
You can find over 100,000 mobile invertebrates per square meter living in and around the kelp stipes and holdfasts.
100,000. Wait, in 1 square meter.
In 1 square meter.
That's like the population of a medium-sized city living in a space the size of your dining room table.
It is incredibly crowded. And because the architecture is so complex, it supports highly specific local fauna that have evolved just to live there.
Like what kind of fauna?
Well, you have the northern kelp crab on the Pacific coast of North America, the kelp fish, and down in South America and the Falkland Islands, you even have the kelp goose.
A kelp goose?
Yeah, a bird that relies almost entirely on these forests for its survival. It is a completely self-contained metropolis.
But, like any great city, it is vulnerable to collapse. And the sources point out a really tragic dynamic here involving sea urchins.
Ah, yes, the urchin barrens.
Right. Specifically, how human activity above the water triggers sheer devastation below it. When nearshore ecosystems are overfished by humans, we pull out the natural predators, things like sea otters and large predatory fish.
If we connect this to the bigger picture, this is a classic example of a trophic cascade. Ecosystem conservation is never just about saving one single species. It's a delicate Jenga tower.
That makes perfect sense.
When you pull out those top predators through overfishing, herbivores like the sea urchin, specifically the green sea urchin in certain northern regions, are suddenly released from their usual population controls.
Because nothing is eating them anymore.
Exactly. Without predators to eat them, the urchins multiply rapidly, and urchins eat kelp. But they don't just nibble on the leaves, they crawl along the bottom and chew straight through the stipes and the holdfasts.
So they essentially take a chainsaw to the base of the tree.
Yes, the entire 260-foot stalk just floats away and dies.
And because there are so many urchins, they graze the kelp forests entirely down to the bare rock. The sources literally call them urchin barrens.
It goes from a towering, bustling underwater city to an absolute wasteland in a very short time.
But wait, I have to ask. Are urchins basically the underwater equivalent of a locust swarm? And if so, isn't it kind of unfair to blame the urchin when our overfishing is what unleashed them in the first place?
That is a very fair assessment. The urchin is simply a beneficiary of an imbalance that humans created. They are just surviving in the environment we inadvertently engineered for them.
Wow.
And that is exactly why groups like the Seattle Aquarium are actively studying this dynamic. They are using remotely operated vehicles, or ROVs, to survey these coastal sites and extract precise data.
Because it's too cold to dive.
Exactly. Humans can't easily spend hours diving in these freezing, turbulent waters, so the ROVs are crucial. They need to understand exactly which micro conditions allow kelp to bounce back and thrive, and why it fails in other areas.
So we can actually design effective human-assisted restoration strategies.
Precisely.
It is wild to think about high-tech ROVs mapping underwater barrens just to save seaweed. But when you have an underwater megacity supporting hundreds of thousands of creatures per square meter, it doesn't just attract marine predators, it attracts us.
Human history is deeply tied to kelp.
Which brings us to the part of the deep dive that really caught me off guard. Humans have relied on kelp forests for millennia. We are talking deep, profound, historical and cultural footprints. Let's start with the kelp highway hypothesis.
This is a fascinating archaeological proposition. For a long time, the dominant theory was that early humans walked into the Americas across a frozen land bridge.
The Bering Land Bridge, right?
Exactly. But in 2007, an archaeologist named John Erlandson and his colleagues suggested an alternative. They proposed that highly productive kelp forests around the Pacific Rim may have actually facilitated the dispersal of anatomically modern humans from Northeast Asia down into the Americas.
And this dates back over 12,000 years, right?
Yes, over 12,000 years ago.
So instead of trekking across a freezing, barren ice corridor where there was basically nothing to eat, they got in small boats and followed a kelp highway.
That is the hypothesis.
That makes so much sense. I mean, ocean travel back then must have been terrible.
That would have been incredibly dangerous. But the kelp forests solved two massive problems for early maritime peoples.
Okay, what were they?
First, as we established, these forests are dense ecosystems. They provided a continuous, reliable food web entirely at sea level. The travelers didn't have to venture inland to hunt. They had a buffet of abalone, fish, and marine mammals right there.
A floating grocery store.
Exactly. And second, and crucially, the physical mass of the kelp forests acts as a breakwater.
Oh, because it slows the waves down.
Yes, it physically absorbs and reduces the wave energy from the open ocean, making the coastal waters significantly calmer. It provided a safer, sheltered corridor for these small boats to navigate.
So kelp literally smoothed the waters and packed a lunch for early human migration. That is incredible. It basically paved the way for human expansion.
It really did. But our relationship with it certainly didn't stop in the Stone Age.
You know, it definitely didn't. Jump forward to the 19th century, and kelp becomes a massive industrial engine. People were harvesting and burning huge amounts of seaweed from the coastal waters to make something called soda ash.
Yes, soda ash, which is primarily sodium carbonate. Before modern chemical synthesis, burning kelp was one of the primary ways to get it, and it was absolutely essential for manufacturing glass and soap.
And the economics of that industry had devastating human consequences, particularly in Scotland.
Yes, during a period known as the Scottish Highland clearances.
Right. Wealthy landlords realized how lucrative the kelp ash market was, so they forced many Scottish Highlanders off their inland agricultural farms and pushed them onto small, brutal coastal plots called crofts.
They intentionally engineered a desperate pool of cheap labor because harvesting kelp before modern machinery was miserable work.
I can't even imagine.
You were talking about people wading into freezing oceanic waters, hauling thousands of pounds of wet seaweed onto the shore, drying it, and then burning it day and night in stone pits just to produce a tiny amount of ash.
And the landlords even petitioned for legislation to stop these people from emigrating away from Scotland because the labor was making the landowners incredibly rich.
It was essentially a captive workforce.
But then technology intervened, right?
It did. A new chemical procedure called the LeBlanc process was widely adopted in the 1820s. It made it significantly cheaper to extract sodium carbonate from common salt rather than burning kelp.
So the market just collapsed.
Practically overnight, the bottom fell out of the kelp ash market. Suddenly, the landlords didn't need that cheap labor anymore.
Leaving all those people stranded.
Exactly. They had thousands of people stranded on barren coastal crofts with no income, which triggered mass emigration. Entire human populations moved from northern Scotland across the Atlantic to North America simply because the price of burnt seaweed crashed.
It is staggering to think that a shift in the seaweed market literally reshaped the demographics of North America.
It's a butterfly effect. The industry did pivot slightly after the crash, though.
Oh, right, for iodine.
Yes. For a time, seaweed remained the only commercial source of iodine, which was crucial for treating conditions like goiter. They would take the kelp ash, wash it, and essentially soak it to pull out the soluble iodine.
Almost like brewing a highly chemical cup of tea.
Very much so. But eventually, terrestrial mineral sources replaced kelp there too, and the major industrial harvesting faded.
But what's crazy to me is that an industry that literally moved populations across the Atlantic has basically vanished from public consciousness.
This raises an important question, doesn't it? How an organism can be so incredibly ubiquitous in our daily lives, yet remain practically invisible to the average person.
Because, spoiler alert, if you are listening to this, you are probably interacting with kelp right now.
The modern applications are staggering in their variety, though I should say, if you look at Asian cuisine, kelp has never been invisible.
It's a staple.
It is a foundational staple. Kombu, which is the species Saccharina japonica, is essential for making dashi, the savory broth that forms the base of countless Japanese dishes.
Oh, I love dashi.
It's delicious. And it's also used to soften beans during cooking. It contains specific enzymes that help break down complex, indigestible sugars in the beans, which actually reduces flatulence.
Okay, that is a highly practical biochemical use. I did not know
A
that.
lot of people don't.
But it goes way beyond the kitchen, too. The sources detail a kelp-derived carbohydrate called alginate. This stuff is basically a miracle compound. It is in ice cream. It is in fruit jelly. It's
Right.
in salad dressing. It's in your morning toothpaste. They even put it in exotic dog food.
It is everywhere.
But wait, if alginate is in everything from ice cream to toothpaste, it must be doing something fundamental to the texture. Is it acting like a sponge?
Exactly.
Yeah.
The mechanism of alginate is why it's so valuable. It has an incredible ability to absorb water rapidly and form a highly viscous gum.
Okay, so how does that help ice cream?
Well, when you put it in ice cream, it binds the water molecules together. This prevents large ice crystals from forming when the temperature drops, which is what keeps your ice cream feeling perfectly smooth and creamy on your tongue instead of icy and gritty.
That makes perfect sense. Nobody wants gritty ice cream.
Exactly.
And the one that really got me, alginate powder, is what dentists use to make the impression molds of your teeth.
Yes.
When they mix that pink powder with water and shove it into your mouth, that rapid gelling process that captures the exact shape of your teeth is entirely thanks to kelp.
It perfectly highlights how seamlessly kelp has integrated into industrial and consumer goods. We extract its most useful properties, its ability to gel, to thicken, to stabilize, and we just strip away the origin.
So you are left sitting in a dentist chair or eating a smooth bowl of ice cream, completely unaware that the structural integrity of that product was born in a turbulent, freezing ocean forest.
Unaware of the underwater megacity.
So what does this all mean? We literally went from a Stone Age coastal migration highway to the dental impressions I got last Tuesday. It is absolute whiplash.
It spans the entirety of human history, really.
It does. It's like finding out the hidden cornerstone of human civilization is just, seaweed. And it even permeates human language and culture in ways you wouldn't expect.
Oh, the cultural quirks are fascinating.
Right. Down in the Falkland Islands, surrounded by these massive ocean forests, the local inhabitants are actually sometimes colloquially nicknamed kelpers.
I love that detail.
And in Chinese slang, there is a fascinating linguistic divide. They use the word haidai, which literally translates to sea waiting, but is a homophone, a pun for kelp.
And how is it used?
It's used to describe an unemployed person returning from overseas who is just drifting aimlessly. They contrast that with hagiri, meaning sea turtle, for someone who returns and successfully navigates the job market.
It is a perfect linguistic reflection of how humans generally view the ocean. The turtle is seen as purposeful, actively navigating the currents to a destination,
Right.
while the piece of broken kelp is seen as being at the mercy of the tide, just drifting aimlessly.
Even though, as we've learned today, those drifting kelp rafts are actually highly effective, biologically engineered mechanisms for global dispersal and life building.
Exactly. The drifter is actually the architect.
The drifter is the architect. I love that. We have covered an unbelievable amount of ground today. For you listening, think about the journey we just took. It's been a long one. We started with a massive biological imposter that evolved completely independently to hack the blueprint of trees. We watched it shapeshift its own body to survive brutal ocean waves, detach to form drifting lifeboats that seed entire continents, and build dense underwater megacities that house hundreds of thousands of creatures in a single square meter.
All under the surface.
And then we pulled it out of the water to see how it calmed the waves for early human migration, triggered 19th century economic collapses that reshaped North America, and ended up magically preventing ice crystals from forming in the dessert in your freezer.
It really is the ultimate invisible engine of our world.
It absolutely is.
And, it leaves us with something vital to consider. Given kelp's astonishing growth rate of 20 inches a day, its ability to thrive in some of the harshest, most turbulent environments on the planet, and its incredibly rapid beta-testing morphological plasticity. Could the genetic secrets of this quote-unquote simple streaminopile hold the key to our future bioengineering and climate resilience? I mean, if kelp already built the highway for early human migration, what future highway might it build for us?